Closing function coverage with deep reinforced learning, compression, and encoder example. Abstract. The simulation-based constraint random coverage-driven functional verification is one of the most prevalent paradigms used on RTL designs today. While greatly enhancing the verification process, reaching a full functional coverage, a necessary step for verification closure, remains a bottleneck. This is mainly due to the necessary manual intervention in the process, consisting of the verification team adjusting stimulus randomization constraint and developing direct tests. This paper tackles the issue by exploring the use and integration of a deep reinforcement learning engine in such a verification environment. Specifically, the technique demonstration here is a deep learning approach Q learning variant named DeepQ network, a similar approach to the one developed in the work of the DeepMind technology to play artery game. The method is adapted to fit seamlessly into a constraint random coverage-driven functional verification environment. The solution development stages along with the simulation result are detailed in this paper. So we conclude by making suggestions in which designs may be good candidates for this novel technique. Section 1 is Introduction. There has been several endeavors aimed at using the ML algorithm to purpose of the optimizing one stage or another of the digital design verification process. See for examples. Unexhausted reviewing presented various ML-based techniques like data mining or inductive logic programming, aiming at generating tests based on the analysis of the simulation coverage data. So using a supervised learning has been conducted in this paper, we specifically focus on a functional coverage closure and reinforcement learning. Reinforcement learning has recently been used in a variety of the applications, and here we present a deep reinforced learning-based techniques that automatically generate stimulus on the fly based on the functional coverage scores achieved during the simulation of RTL design. We emphasize here that conceptually, RL algorithms are different from the supervised learning ones, as the training data for RL algorithms is generated on the fly as an inherent part of the learning process itself. This is further discussed in Section 5. The paralleling core concept between the RTL verification and reinforcement learning is first classified along with the role and the integration with the reinforcement learning agent in a modern SystemVerilog-based verification environment. The design used in this experiment is LGW compression encoder with the written in a SystemVerilog RTL. This design is on one hand sufficiently complex to be representative of a typical RTL verification process, and on the other hand, it allows for an ambiguous assessment of the approach's benefit of the closing functional coverage. We then present a solution for co-simulating efficiently our deep reinforced learning agent coded in the Python PyTorch and the rest of the verification environment written in the SystemVerilog. The DQ learning agent itself, implemented as a DQN, is presented in the section that follows. We report the result of the co-simulation on the LGW compression encoder and show the use of the integration of DeepQ learning-based technique is efficient. It's automating the generation of the test generation in forms of the transaction and sequences of the transaction that are necessary to hit the most tenacious functional coverage beams of the design and paving the way toward the verification closure. Section 2 is RTL verification and reinforced learning. As a RL, a system can be thought of the sequential decision-making process where the information between the RL agent and the RL environment is exchanged. At every timestamp t, and the RL agent executes an action AT on the RL environment. AT itself is a function of the RL environment current status ST and the reward RT, which is a scalar value both obtained from the previous RL agent action AT-1 and A to bring the RL environment to a new state. The as t plus 1 is the new reward values are t plus 1. This data used by the RL agent to learn what subsequent action shall be selected at the next time step with the constant objectives maximize the expected future reward as received by the RL environment. The learning processes executed by the RL agent can either estimate a policy function pi, which is a direct mapping of an RTL environment state to an action, or of a value function. A value function is given a specific policy function pi, return the expected reward of the being in a state and taking actions according to the pi. We focus on this paper on a special value function called the action value function. Q. Our Formula 1 is the action value function. Q pi as A is E R/A S and pi. In words, a given policy pi, this function accepts a state and action and returns the expected reward of the being in the state and taking this action. We now transform the RTL verification realm where we specifically focus on the functional coverage closure problem. Firstly, digital simulation can be described as a sequential process which generates a series of input transactions and different timestamps. These input transactions are driven sequentially through a design under test DUT and processed by the DUT, and DUT generates a transaction in return. The subsequent generation of the stimulus in the form of the input transaction to the DUT can be made dependent on these output transactions or any other effect of the previous input transaction had on the design. Therefore, digital simulation can be described as a sequential decision process similarly to an RL system. We now apply the following translation regarding the RL problems concept. We first consider a typical modern test bench TB as depicted in figure 1 by focusing on the entity represented by rounded corners rectangles. Figure 1 is the RL agent and RL reinforcement learning is the environment in a typical test bench. So an intelligent test bench entity that is responsible for generating new stimulus is transformed into our RL agent. The DUT along with the non-stimulus test bench's entity form the RL environment. So the RL agent generates and drives the input transaction to the RL environment. These are these actions. So that the RL environment generates on the fly on a score which is proportional to the functional coverage bin hits that occurred because of the given input transaction. This is the reward. The objective of the RL agent is to hit as many functional coverage bins as possible. This process reaches the termination condition once we reach the full functional coverage. Before we address the RL environment state, we call here the RL problems and models as a Markov decision processes and need to exhibit the Markov property, meaning to the current RL environment state only, that it contains enough information for the RL agent to select the optimal actions in the view to maximize the future reward. We focus here on functional coverage closure, so our RL environment state is at every timestamp t, either the representation of a functional coverage state, what bins have been hit, and how many times, or Markov representation of the input transaction of created such a coverage state. So the Markov representation is clarified further with our LGW compression encoder as example. So we also show the translation of the action value functions Q phi S and A. This is a functional coverage closure problem. We emphasize here, the RL environment state is not a DUT state as a presentation by the concatenation of its sequential elements. We also remark here the generally a typical functional coverage definition for a given DUT generally includes include various categories representing the features of the design. So, using our approach, every category shall be represented by its own action value function. So section 3 is the LGW compression encoder. Our duty is an LGW compression encoder, which architecture is depicted figure 2 below. So the figure 2 is the LGW compression encoder. The LGW compression encoder receives the input sequences of 4-bit symbols and uses a 16 address content addressable memory (CAM) to perform the dictionary-based compression lookup. So hence the compression output sequence is composed of 5-bit symbols to represent the 32-bit symbols. So 16 original input symbols and the 16 CAM addresses. The CAM is cleared every time an input sequence starts. It then gets populated anew along with a new input sequence. So to demonstrate the CAM population process, we consider the following sequence of 4-bit hexadecimal input symbols. Start A, B, A, B, A, B, A, and end. Transition 1 is the input sequence example. Table 1 details the compression and output generation process. So the table 1 is compression and output generation processes. The above 8-bit input sequence is compressed into the following 20-bit output sequence. The transition 2 is output sequence example. Start O-A, 0A, 0B, 10 and 12 and end. Note that the input output symbol is a CAM address. It is preceded by a 1, otherwise it is preceded by a 0. As we reset the CAM before every new sequence, the maximum number of symbols that can be overwritten to CAM0 is 2, which is the smallest input sequence. Now we consider CAM1. If we got the CAM0 match using the second and third symbol of input sequence, so we can populate the CAM1 with a maximum of 3 symbols. So this happens only if the 3 first input symbols are the same. So with the same reasoning, the maximum number of symbols can be overwritten, that can be written to CAM15. So CAM15. So which is the highest CAM address is 17. So it will happen with a sequence of the same contiguous input symbols, precisely 137 of them. See figure 3 for the LGW compression encoder, top level waveform for compressing the sequence above. The figure 3 simulation waveform is AB, 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 is 0A, 0B, 10, 12. Note that we have used the Arlec Rivera process research edition for the user simulation and this research. Figure 4 is below that depicts a simple version of the CAM area, memory area. Figure 4 is simplified the CAM memory area. So we now consider the LGW compression encoder functional coverage and focus on the CAM right functional coverage. We define the bins of this category as follows. For every CAM addresses, we want to exercise writing every possible input sequence length. So the CAM0, this is the length is 2. So for CAM1, this length is 2 or 3. The CAM4, for CAM15, this length is 2 to 17. We now evaluate the number of the functional coverage bins below. The CAM can store the 152 input bin symbols of 4-bit each to input symbols at CAM0 and up to 17 and CAM15. Hence, in the total the CAM, hence in total, the CAM can store the 2 plus 17 divided 2 is multiplied by 16 equal 152 input symbols. Now the smallest input sequence written to the CAM is is over two input symbols so as far as the cam right functional coverage is concerned. They represent one bin. Hence, we have one bin at cam 0, two bins at cam 1, and up to 16 bits at cam 15. So this gives us in total 1 plus 16 divided by 2 and multiplied by 16 is 136 cam right functional coverage bins. So that the input sequence patterns necessary for hitting all these functional coverage bins are very specific, and reaching them randomly is unlikely, as shown below using examples. For instance, the following input sequence pattern can hit the three inputs written to the CAM3 functional coverage bin. Transition 3 is the input sequence example for three symbols in CAM3. Start A, B, C, 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 and AB is written to the CAM0, BC to the CAM1, and CC to the CAM2, and CC is matched to the CAM2, and finally CCC is written to the CAM3. Indeed, catching the three right location in CAM3. The next pattern can hit the three symbols written CMPA for functional coverage bin. Start ABBB, ABC, DDDDD, and the transition 4 is the input sequence example for three symbols in CAM4. The AB is written to the CAM0, BC to CAM1, CD to CAM2, DD to CAM3, and DD is matched to CAM3, and finally DDD is written to the CAM4. The indeed caching the three right allocation in CAM4. During the standard constraint random verification process, it's not improbable to hit all the functional coverage bins by using the random input symbol generation. In fact, using a uniform distribution to generate our 16 different input symbols for bits, we have generated for hit a maximum of the only 28 CAM right functional coverage bins out of the 136 bins, using a substantial amount of the input sequences. So, closing the remainder of the CAM right functional coverage bins, next state from a vacation team on internal knowledge of the design and the development of the customized and tracked test. We demonstrate here how an RL agent can, by learning from the RL environment state as per the definition in the section 2, the VB and the previous functional coverage hits the transformed into real-world values, generate automatically the input sequences necessary to achieve the full CAM right functional coverage. So the DUT implementation is resident on the GitHub and available upon direct request, C13. The section 4 is called simulating the RTL design and the DQ running agent. Before we detail the implementation of our functional coverage closure DQN agent, we mentioned here that Python PyTorch library was used for the purpose of modeling it. PyTorch is an open source framework efficient for building deep learning models by providing automatic differentiation. On the other hand, our TB is described in SystemVerilog, and DUT is modeled using a SystemVerilog RTL subset. Therefore, we face the obstacles of co-simulating our DQN agent with our original verification environment. To address this issue, we developed the architecture described in Figure 5. The Figure 5 is the co-simulation architecture. And the main idea behind this architecture is that we have two independent processes which are launched simultaneously and run concurrently. The first process is the digital simulator and would normally run in an RTL simulation, and the second one runs the DQN agent. The DQN agent awakes from the reset in the standby mode and are ready for each learning process. It awaits to receive the state from the RL environment and then provide back an action based on output of the FFNN implemented in the RL agent. The subsequent state and the reward received from the RL environment as a consequence of this action are first used to optimize the parameters of our FFNN. The optimization algorithm is the DQN process is described in section 4. After this optimization step is executed, the same state is fed to our newly optimized FFNN to generate the new action. This completes a full learning iteration. In terms of RTL verification, this learning iteration is one input transaction driven to the duty and the processing of its impact of the functional coverage and the view of generating subsequent stimulus. The communication between the digital simulator and DQN agent is achieved using a SystemVerilog direct programming interface DPI and its embedded Python code. So the RL agent opens the server socket using the Python socket library and then listens continuously for any activity on the socket. The RTL environment behaves as a client on the socket, and whenever the RTL environment state and the reward need to be sent to the DQN agent in order to receive a new action, the RL environment connected to the socket and the RL agent learning iteration process starts as it listens continuously to the socket. So the socket is depicted in the ellipse in the figure 5. The implementation-wise, we used custom encoding for the state, the rewarding, and the action using a size configurable arrays of 8-bit integers. On the SystemVerilog side, we define the following imported DPI-C. The code snippet 1 is the SystemVerilog 2 from Python and PyTorch. The sizes of the communication arrays are set on the fly during the above two-way communication. The SystemVerilog TV and the communication implementation are resident in the GitHub and available upon a directory cast C13. The section 5 is the DQ running agent. Figure 6 shows the full implementation of the DQN agent. So the DQN agent like this. The LGW compression encoder processes every clock cycle a 4-bit input symbol and belonging to an input sequence. The C figure 3.4 waveform is description of this process. The action provided by the RL agent to the RL environment is eventually translated into what input symbol shall be driven to the duty in the next clock cycle. The RL environment state is a self-representation of the last 17 input symbols as received by the duty. A series of 17 input symbols is the largest write value and the largest match value, and the LGW compression encoder, the CAM process. Both write and match occur on CAM 15. See figure 4. A sequence of input symbols is directly responsible for the way and the CAM gets populated. We defined further the reward function, which is principal and return a high value, and the more input symbols are written or matched into CAM. By using both state and the reward, DQN agent shall generate symbols to achieve a maximum reward, which in terms of verification means shall coverage toward functional coverage closure. Figure 7 shows the representation of the RL environment state. It is a 69-bit binary vector. Every input symbol is a 4-bit, and the MSB and the valid bit signals the toast port reset state. So the figure 7, the RL environment state. The RL agent RL agent is in score a 4-layer FFNN that processes the 69-bit RL environment state vectors as defined above and produces as a system element of vectors. Each element QSA of this of vector is an action value scalar, and QSA defined as the expected future reward in the state S. If we execute the action, every action is equivalent to driving a specific input symbol. We showcase the FFNN using a starting diagram 12 and figure 8. Figure 8, the FFNN for the DQN. So the reward itself, in the context of our CAM right functional coverage problem, is defined as follows. If the driving input symbol causes no CAM activity, the return reward is null. Otherwise, there are two cases. CAM right, if the if can write the reword is number of the input symbols written at the CAM address, can match the reverse is number of valid input symbols at the CAM address plus 1. We avoid the additional point of CAM match on the account of such an event potentially enables subsequent larger CAM write event, so we use the E greedy policy denoted as a file in section 2 on the FFNN, the 16-element action value of vector. The policy selects the probability epsilon symbol I, the input symbol, randomly or with a probability 1 minus epsilon, the symbol equivalent to a maximum FFNN vector output. This symbol is driven to the RL environment. This results in a U state as I plus 1 and a reward R provided by the RL environment. Before using the new state as I plus 1 eventually generate a new symbol, new input symbol, we executed optimization past our FFNN in the view of the mixed margin to the rows, the symbol between the symbol I, the originally expected reward state S, and a re-evaluation of the symbol I's expected reward in state S, which uses the actual received reward R. For this purpose, we use the Q rounding update rule, and the formula 2 is the Q rounding update rule. Where the alpha is the running rate, gamma is the discount factor, and the max Q, Si plus 1 is A is the maximum Q as A after value is given to the by the FFN before the updating its parameters to rows, parameters on the rows C, 6, 7, 8. In the next section, we detail the actual values used for the Q rounding updated rate update rule during the simulation. Using the Q rounding update rule, the action value function Q implemented in the FFNN is optimized on each iteration. The policy pi used in a DQN agent is epsilon greedy and the decreasing the value throughout the episode epochs. And an example is demonstration in the next section. The learning process is DQN is fully independent of the policy. Such algorithms are called off the policy algorithm, as the policy choice has no bearing the prediction accuracy for the action value function QSA. So the RL agent PyTorch implementation is resident on a GitHub and available upon the direct request C17 and C13. Section 6 is the DQN simulation result. First, we call here the standard constraint random simulation with a uniform distribution used for the input symbol generation brought us a maximum of 28 bits out of the 137 CAM right functional coverage bins with a CAM overall occupancy of 44 out of the 152 CAM location. In a standard process, the next steps would be a manual turning of the constraint and the writing series of directed tests to address functional coverage holes. We now report DQN use performance on the CAM right functional coverage. During the digital simulations, the post-reset RL environment state is constant and is also the same as between two contiguous input sequences. Hence, an epoch always starts from the same RL environment state. This is also the first value driven to our FFNN. Moreover, every input symbol generate an RL environment state transition as per our definition, creating a constant feedback for the DQN learning process. We run an episode at epoch equivalent to an input sequence until the LGW compression encoder CAM is full. This is because subsequent input symbols in the best case would return matched but also many null reward, and this could deteriorate the learning process achieved during the CAM population. We first start with a simulation that are 500 episode epochs with a linear decreasing epsilon 3D value ranging from full exploration 1.0, where all input symbols are selected randomly, to full exploitation 010, where all input symbols are selected based on their expected reward as shown by the FFNN alpha vector. As for the Q learning update rule, we set the learning rate to the 100th, 1.00 e minus 2, and the discount factor to 0.75. We first bring below the figure 9 the FFNN loss over the generated symbols. We can observe that it takes around 500 symbols for the FFNN to converge on a low and constant expected reward estimated. We quote here that our goal is to close to the CAM right functional coverage, hence we want the DQN agent to generate sequences of input value symbols from the exploration to exploitation until we reach the following determination condition. Or 1 in 36 CAM right functional coverage bins have been hit at least once. The figure 10 is the simulation report after the 500 episodes. That we observed we have managed to hit 1 in 33 out of the 1 in 36 CAM right functional coverage bins. This is an excellent result compared to a standard simulation with a uniform distribution of the input symbols, which achieved a maximum of 28. Figure 10 is a 500 episode and final simulation report. We now refer to the last RL environment state appearing to the state LGW sequence line-in. Figure 10 is really marked this sequence of the input symbol is appropriated to populate higher CAM addresses on the account of the full coverage almost achieved. It's possible that a DQN agent started generating short repeating the sequence in the first episode and epoch, and the longer and longer ones as the simulation went through an episode epoch. We investigate this point further with the exploration on figure 11. The three last missing bins in this simulation are following ones. CAM 13 is right 10 symbols, maximum 15. CAM 15 is right 12 symbols, maximum 17. CAM 15 is right 14 symbols, max 13. So we figure 11 below the report how many CAM's locations have been written to the maximum is 1 in 52. Is throughout the input symbol generation. The black horizontal line in figure 11 and also figure 12 represent the maximum score achieved via random uniform distribution of our input symbols. Thus, figure 11 is a 500 episode or epoch, the CAM overall occupancy. In total, we have 1 in 52 CAM location, and figure 4 is because an input sequence written to the CAM is a minimum of 2 input symbols. It gives us a 1 in 36 CAM right functional coverage bins. Back to figure 1, we can see at the beginning of the process that around 32 locations get filled very quickly. This is because the input symbol generation process is fully random at the beginning of the full exploration and generates mostly non-repeating the sequence of 2 input symbols. Then slowly the learning process kicks in, and we can see the quasi-linear population of the CAM location, meaning of the DQN agent generated longer and longer repeating input sequences until it managed to occupy the whole CAM with a long enough sequence of repeating input symbols. To see the sequences of the trees reported in figure 10 is note that toward the end of simulation, when the occupancy reaches to 1 in 40, we can observe a jump. This points to the fact that we functional coverage bins have been skipped, as indeed reported in figure 10. To limit the 3 remaining uncovered CAM right functional coverage bins, and instead of developing a directed test, as we would in a standard verification process, we run a DQN simulation with 1 in 7 and 50 episode and epoch. This should allow for a smoother transition from exploration to exploitation, as described later for epsilon is lower than the first simulation. Figure 12 shows the camera overall occupancy throughout the test for a 750 episode simulation. So the figure 12 is 750 episode and Apple's cam overall occupancy. The 750 episode Apple's DQN simulation hit 1 in 27 functional coverage bins, but most importantly, hit our coverage holes. By merging the functional coverage result of both simulation, we will achieve the full cam right functional coverage result for the LGW compression and encoder. For the sake of comparison, figure 13 shows the cam over the occupancy for a standard verification process with the uniform inputs symbol distribution. And figure 13 is the cam over occupancy with a random uniform input distribution. We see the same steep curve corresponding to a long sequence of two input symbols throughout the cam address range. The most of the time there are no improvement to flat line unless the sequence 3 of the 4 possibilities randomly repeated causes a little step. Using many input sequences above 750 to populate the cam, we have achieved the maximum of 44 compared to the full cam population and full cam right functional coverage for DQN approach. The section 7 is summary and conclusion. Other has been previously used for a range of applications, and this paper, we introduced the use of the adapted DQN agent in the context of the modern RTL verification process. During a standard simulation based on constraint random coverage-driven functional verification, the LGW compression encoder used as a DUT in our experiment would require substantial manual intervention to create a stimulus necessary to close the cam right functional coverage. It took our DQN agent to a series of epochs, 500 and then the 750 to reach the cam right functional coverage bins. The result was achieved during the standard regression process in terms of simulation time and computing resources. We believe this positive result paves the way of the broader use of both the verification environment achievement used in the paper and the DQN agent, including the context industry semiconductor project. Good design candidate for this paper approach the RTL design and shows reluctant to achieving a good functional coverage result using a standard verification process and requires a substantial amount of the manual intervention to tune the randomization constraint to develop the direct test. So, today I'll write this paper from the DVCON2023. The paper was the closing functional coverage with deep reinforcement learning, a compression encoder example. Thank you for your time. See you next time.